Yeah, thank you, Dr. Ibtisam, for introducing me so nicely. And I'm also thankful to the whole organizing committee for actually inviting me to as the keynote speaker in this actually prestigious conference. So, good morning to all of you. Good afternoon. So, I'm going to speak over the multi-component systems or the heterostructure for scalable green hydrogen production using overall catalysis. Actually, my research lab here actually at Jamia Millia Islamia. Yes, we are working over the green hydrogen production as well as for the CO2 reduction reactions or the nitrogen reduction reactions. So we are applying the three major routes like actually photocatalytic, electrocatalytic and photoelectrocatalytic methodology, and continuously publishing actually good number of the papers, and the CV actually that is actually read by the moderator. It is quite actually old. So presently actually my citation actually touches to 10,500 with an actually Python index of 194 and H index of 61. We are also working actually over the like gas sensing properties or the applications of these advanced materials. And also, actually, we are doing some organic transformations reaction which were actually supported by the metal oxide based nanocatalyst, and we are actually producing a large number of actually valuable chemicals through this method. The basic theme of our actually research actually is to design the advanced catalytic systems for their multifunctional application. And this actually, the class of the work actually that we are doing, it is actually best fit and best match to the theme of this wonderful conference. So why we are actually having so much of interest in hydrogen? Because actually, if you could see globally, you could see the energy of crisis, and there are actually n number of the factors are associated with the crisis of the energy, like the high demand of the energy supply, poor infrastructure, excess wastage, high population growth, political instability, limited renewable energy sources. So actually, these are the factors. So this area actually needs the mediation, and hydrogen is considered as one of the alternate source of renewable energy because it is a clean fuel and green energy. When it is consumed in fuel cell, then it produces only water, electricity, and heat. It is carbon free and highly abundant. It has more energy as compared to the gasoline. It is environmental friendly and has zero impact over the environment. Therefore, the overall water splitting, like actually photo electro and the photo electrocatalysis, they are considered as the most prominent methodology of water splitting to produce economical green hydrogen to resolve these energy crisis issues. Basically, water splitting is a simple chemical reaction where actually you can break water molecule into elemental hydrogen and the oxygen. The reaction actually looks very simple as actually I'm showing in this slide, but this reaction is not as simple as actually it's projected over here. Generally, the splitting of water occurs actually in presence of the catalyst, and other driving force is the actually presence of the light source. So to make actually economically viable, then actually to you have to make all the process cost effective. So we actually then then the solar spectrum, solar light actually is the simplest light source. So if you see the solar spectrum, then you could see actually the visible light component is around 46 to 47%. So if we are able to design the advanced uh, nanomaterials, heterostructures, which are active under visible light, means which are having actually the optical band gap in the range of 1.8 to 3.2 electron volts. So we have to make some chemical modifications either by doping or by designing some heterostructures so that actually we can do optical band gap tuning to bring their optical band structure in the visible range. And secondly, they should be in the small grain size so that they will have the large surface area, means the large active sites for the catalysis, and you need to inhibit the recombination of the electron mode pair. Then actually it's very prominent for the scalable hydrogen production. So this is the experimental methodology how to generate hydrogen. in the water splitting phenomena. So just first actually you have to prepare the advanced material, then you have to take the advanced material into the specialized glass vessels and add with the sacrificial agents, then apply the light source. So actually the intensity of the light actually depends on the optical band structure of your material. So we have to use the different band path filter to fix the intensity of the light source. Then at a particular wavelength, this actually the irradiation occur over the solution where the photocatalyst absorbs the light and it can actually allow the separation of the photogenerated electrons that are actually went to the conduction band and whole pair remain in the valence band. And there must be actually inhibit the recombination of the electron hole pair, and the electrons that are used, they reduce H plus into the hydrogen molecules, and holes are utilized to oxidize water to produce oxygen. So the another methodology that we use for water splitting is the electrochemical water splitting. Electrocatalysis actually this methodology is very simplest method which is known for the water splitting from a long time back, where it actually involves three electrode reaction where you can use the direct current to separate hydrogen and the oxygen. Generally, the hydrogen evolution reaction, HER reaction occur at cathode, whereas OER oxygen evolution reaction occur at anode. So if you just make some kind of the transformations, like if you use the light source, then actually the kinetically the reaction rate become more faster. This methodology then is called as the photoelectrochemical water splitting. So this is the three electrode system reaction where actually you can make the working electrode with the help of your the suspension of your material, and then you have to use this methodology to make the process economically viable. So basically, the thought process of this research actually, our research actually is based on the green hydrogen production. For that, we have to actually design and make the noble metal-free, cost-effective catalyst. And because actually, if you really interested in this system, then the costing actually is very important. Costing and the scalability, because these are the actually experimental parameters. For that, actually, you can take the ideas of how to where you have to actually achieve and where you have to go. So we have to design the metal-free catalyst by taking the graphene oxide and the reduced graphene oxide at the or the graphite carbon nitride, like the carbon support, and the TMCs as the other support of the oxides to make binary and the ternary heterostructures, and then apply the photocatalysis electro and the photoelectrocatalytic applications of these materials. So if you are actually really interested in these kind of the research, so for these heterostructures, when you actually mix the two or more than two semiconductors, then they form actually different kind of the photocatalytic systems. So here actually we are more interested in the like actually uh, generation 2 type of the photocatalyst, where actually in the generation 2 photocatalysts, they actually show the different kind of the charge transfer dynamics, and the different kind of charge transfer dynamics. Very important actually when you comment over actually the scalability of the hydrogen production, because actually you need to have the free electron for that one, and the charge transfer dynamics, whether actually it belong to type 1, type 2, type 3, scheme, or these. This is also very, very important. Otherwise, actually, you can't actually comment over why actually this material gives the more scalability or more hydrogen production as compared to the other materials. So this chemistry actually important for this kind of the material. So graphene oxide, reduced graphene oxide, and graphite carbon nitride, these are an important material as a support the heterogeneous catalysis because of their unique properties like excellent potential in the environmental remediation reaction. These are the structures and the properties. They are having the different band gaps. So according to their different band gaps, we have to take their support to make the binary and the ternary heterostructures. And these are some properties of the transition metal chalcogenides, TMCs. And TMCs actually are having the tunable like catalytic properties, stability to make them attractive candidates. And uh, uh, they can provide the active sites for the HER reactions, and they are some of the properties that how these TMCs are important. It was actually summarized here or in this slide. Now, actually, with the help of these components, you can make the binary or the ternary heterostructure. So during the formation of the binary or the ternary heterostructure, there is actually increment in the active sites, and there is actually tuning of the band structure or the band properties, so that actually they can actually improve their catalytic active sites due to synergistic effect, and there is improvement in the kinetics, so that actually it can actually give the high hydrogen production. Great. So this is actually a very simple slide. Everyone knows about it. Actually, for the designing of the material, the chemical and the physical methods are very important. And here, actually, being a chemist, we generally use the chemical methods like sol gel, polymer, citric, cursor, sol, solvothermal. Means actually a number of methods are there. So to design the material for these properties. So the strategy of the material selection is also important. Like actually you have to look what kind of the effects actually you are interested, what kind of the properties you must look for. Then what should be your target parameter? Like for example, if you are really interested in the high hydrogen and the oxygen amount, then you have to look for the lifespan of the electron hole pair. For the actually efficient charge transfer, you should look for the high mobility of the charge carrier. Then crystallinity becomes very important for homogeneity and the high absorption, the crystallinity as well as the small particle size are the important target parameters. So accordingly, actually, you can fix your mind actually and then go for their actually properties and other kind of the application. So in this series, so for this actually hydrogen evolution business, first actually I'm going to show the graphite carbon nitride as one of the carbon support. Why we actually chosen graphite carbon nitride? Because it is an ideal candidate for photochemical water splitting due to its excellent alignment of its band edges with water redox potential. So this actually graphite carbon nitride was prepared by taking melamine, and if you anneal melamine at around 520 degrees centigrade temperature, then it forms actually bulk graphite carbon nitride. And if you exfoliate bulk graphite carbon nitride in fuming sulfuric acid or fuming HCl, then it forms very beautiful honeycomb like highly porous nano sheets of the graphite carbon nitride, which could be actually seen in these uh, detailed electron microscopic images, and the tilting of the sheets during exfoliation could be seen in the FESEM images. So before going to the HER business, we should do the primary investigations like we do X-ray diffraction, we do the T surface area investigation, UVDR for optical band gap, PLTRPL, and the XPS investigation. Then for the hydrogen evolution reaction and the photochemical water splitting, we have made the two sets of the reaction. In one set of reaction, we have taken the trithenolamine and the sacrificial agent, and in another set of reaction, we have taken the combination of the sodium sulfide and the sodium sulfide, and we have observed that the trithenolamine as the sacrificial agent is able to produce 470 micromole per hour per gram of hydrogen with an apparent quantum yield of 12%, whereas actually the sodium sulfide uh, sacrificial agent is able to produce 230 micromole per hour per gram of hydrogen with an apparent quantum yield of 7%. So now actually these materials could be used for photoelectrocatalytic activity towards HER reaction. And here if you could see, this is the LSC plot for the HER and then LSC plot for VR. And the downside actually C plots belong to the taper slope plot, and the last one is the turnover frequency plot. So these actual investigations suggest that the high HER current density in presence of acidic medium could be observed, and the all low onset potential in the acidic media suggests for the high photocurrent density for that requires for less voltage for the hydrogen evolution, and the low value of the taper slope shows the significant HER reaction, and the intrinsic activity of graphite carbon nitride nanosheets was estimated for the determination of turnover frequency for HER. Then we have actually taken these graphite carbon nitride nanosheets to actually mix with the copper ferrite nanoparticles to make the type 2 heterostructure formation of these copper ferrite with the graphite carbon nitride. And we have mixed the graphite carbon nitride in the copper ferrite and the graphite carbon nitride in 10, 20 or the 30 weight percent ratio. This is the actually synthesis protocol for making these binary heterostructure. So the primary investigation and the primary characterization is very important. And if you have understanding, very good understanding of the actual diffraction, you can actually index each and every phase of any kind of the heterostructure. Then do for actually like you do UEDRS, you do for PL, you do SPS and the BT surface area investigations. Now coming to the photocatalytic water splitting studies. So here for again for this one actually make the two sets of the reaction in one set of reaction. Trithenolamine was the sacrificial agent and in another set of reaction the sodium sulfide and sodium sulfite was the sacrificial agent, and it was observed that the in presence of the trithenolamine as sacrificial agent, the 28% loading of the copper ferrite over graphitic carbon nitride is able to produce 1 millimole per hour per gram of hydrogen with an apparent quantum rate of 25%, whereas the actually high loading of the copper ferrite nanoparticles could actually reduce the light absorption by highly porous graphitic carbon nitride nanosheets and thereby decreasing the formation of the electron hole pair. And here actually we could explain the charge transfer dynamics for the formation of the binary atom structure. So in the electronic impedance spectroscopic plot, you could see the low semicircular image suggests for the low charge transfer resistance for copper ferrite, graphite carbon nitride heterostructures, which leads to enhanced interfacial charge transfer over the surface of the heterojunction. And with the help of the Mott-Schottky plot, we have been able to calculate the nature of the material. For example, the positive Mott-Schottky plot in the graphite carbon nitride suggests for the n type of the semiconductivity, whereas the negative Mott-Schottky plot for copper ferrite nanoparticle suggests for p type of the semiconductivity, whereas positive as well as negative Mott-Schottky plot suggests for the p-n heterojunction formation for the copper ferrite graphite carbon nitride heterostructure. And there is a decrease in the PL intensity which actually on increasing copper ferrite nanoparticle with 28% loading of the copper ferrite over graphite carbon nitride suggests for the low recombination of the electron hole pair in the 28% loading of CFO with the graphite carbon nitride. And if you look for the band structure mechanism, then you could see actually before mixing the copper ferrite with the graphite carbon nitride, the band positions of the copper ferrite and the graphite carbon nitride in terms of the valence band and the conduction bond actually is different. And when you mix both of them, there is actually Fermi level alignment. And during the Fermi level alignment, the electrons that are present in the conduction band of the copper ferrite nanoparticles tunnels towards the low conduction band of the graphite carbon nitride, and whereas the holes from the valence band of the graphite carbon nitride tunnels towards the valence band of the graphite carbon nitride. Copper ferrite nanoparticle. This type of the actually charge transfer, this suggests for the type 2 heterojunction formation for the uh, copper ferrite with the graphite carbon nitride heterostructure. So then now coming to the electrochemical water splitting investigation. So here actually you could see actually the OER plot, LSA plot for OER reaction, and the corresponding Taposilo plot is shown over the right hand side, and the low side you could see the HER LSA plot for HER reaction and the corresponding Taposilo plot over the right hand side. Here actually these investigations suggest that the improved current density, low potential were copper ferrite with the graphite carbon nitride heterostructure reverse for the copper ferrite nanoparticles not only increase the charge transfer but also increase the active site for the water splitting reaction. So here actually again these binary heterostructures could actually exhibit the high HER activity as compared to the pure graphite carbon nitride, and we have been able to obtain the high Frederick efficiency, which is close to 95% for these material. Now another binary heterostructure is the copper oxide with the graphite carbon nitride. Here again, this is also indexed in the type 2 formation. And the synthesis protocol, X-ray diffraction, and some data over the surface area and band gap investigations. I have presented over here. This copper oxide nanoparticles was actually simply prepared by the hydrothermal method and then by simple mechanical mixing, then forms the binary heterostructure. Then it could see actually if you see the structures of these actually graphite carbon nitride and the copper oxide nanoparticle, then actually One is having the cubic structure and other is having the hexagonal form. And when you actually mix both of them, then there is structural transformation for the orthorhombic phase formation. And during this phase formation, we could see that the conduction band of graphite carbon nitride become more uh, populated, which actually helps to actually explain why actually the 38% loading of the copper oxide over graphite carbonate could give the high amount of the hydrogen production, which is actually 3.5 millimole per hour per gram of hydrogen with an apparent quantum yield of 18%. In fact, we are the first actually who have reported this kind of the result with the copper oxide nanoparticles. And interesting results we have added in the literature when we do the electrochemical HER and the OER reaction. So we have actually done the HER and the OER investigation and compare all the results with the iridium oxide commercially available electrocatalyst, and we have observed that either most of the parameters are comparable or better than the iridium oxide. So we have shown the possibility that the uh, copper oxide nanoparticles with the graphite carbonate could be the best replacement for the commercially available iridium oxide. Then we have actually designed and make the cadmium selenide. We have actually grown up the cadmium selenide quantum dots of graphite carbonate, quantum dots over the graphite carbonate sheets by with the help of the Szilard cycles. And on the basis of the number of the Szilard cycles, we have classified these materials as 10, 20, or 30 in terms of the number of the Szilard cycles. So with this material actually was investigated with many techniques, because actually for the catalysis type of the paper, you need to actually show many techniques like actually do the X-ray diffraction, UV-DRS, XPS, VAT, then PL, TR, PL, technically PR, and the yes, so we have actually added all the investigations here, there, actually in the paper. These are the actually detailed electrochemical, electron microscopic studies. Here actually, I will not go into the detail, but actually the heterostructure formation at the interface could be seen in the HR team images. So here, the 30 Szilard cycles of the cadmium selenide quantum dots is able to produce 4.3 millimole per hour per gram of hydrogen with an apparent quantum yield of 24%, which was actually supported by other investigations like actually EIS, photocurrent plot, and the PH investigations. Then the 30 Szilard cycles of the cadmium selenide quantum dots for graphite carbon nitride is giving the significant HER reaction, which was actually supported by the high electrochemically active surface area. Now coming to another binary heterostructures. Here again, actually, we have, and actually in the previous slide, actually the band structure mechanism belongs to the Z scheme. So here actually cadmium sulfide quantum dots that are actually grown up for the graphite carbonate with the help of the Szilard cycle, and the charge transfer dynamics suggests for the type 2 heterostructure formation for this cadmium sulfide with graphite carbonate heterostructures, and we have actually reported for the efficient photo and electrochemical hydrogen production. So here actually the 30 Szilard cycles of the cadmium sulfide of graphite carbon nitride is able to produce 14.8 millimole per hour per gram of hydrogen with an apparent quantum yield of nearly 28%. And here actually the 30 Szilard cycles of graphite cadmium sulfide over graphite carbon nitride to show the significant HER reaction, which actually supported by the high electrochemically active surface area. And the interaction between the graphite carbon nitride and the cadmium sulfide quantum dots could play a crucial role for the spatial charge transfer on the heterojunctions of the material, which improves the catalytic activity. And then this is the MOS2 nanoflowers that actually we have made with the help of the hydrothermal method. Then by mechanical mixing, they were mixed with the graphite carbon nitride to make the 10, 20, and 38% the ratio of the MOS2 with graphite carbon nitride binary heterostructures. And this is synthesis protocol actually how we have formed these beautiful nanoflowers of the MOS2 with the graphite carbon nitride. And here actually the 28% loading of the MOS2 or graphite carbon nitride is able to produce 18 millimole per hour per gram of hydrogen with an apparent quantum yield of 34%. And remember, actually, in all the investigation, the post-catalytic studies and the stability of the catalyst is also very important. So for that, you need to remember you have to do the X-ray diffraction studies, the scanning electron microscopy studies, and the XPS studies to actually show the post-catalytic stability of the catalyst for this kind of the reactions. So 28% loading of the MOS2 or graphitic carbon nitride could exhibit the high HER activity supported by the high electrochemically active surface area of this material. So not only actually these materials, we have actually added many reports in the literature. For example, we have made the TiO2 MO3 based multifunctional catalyst, which are actually thermodynamically stable, and we have shown that they could have the actually multifunctional applications in hydrogen energy production as well as actually ammonia gas sensing applications. Also, we have actually added in the reports like actually ternary heterostructures based on MOSC2, nanoflowers with the zinc sulfide. And this paper actually are getting very high traction in the literature. Then we have made the quaternary heterostructure. Very important system actually we have actually added like actually TMO, TE2, MOSC2, then as well as TMO, TE2, MOS2. So then this type of the quaternary heterostructure we have actually added, and we have actually studied their very interesting ultra fast charge transfer dynamics to actually support for these kind of the investigations. We have actually added many papers actually based on the multiferric oxides, like actually we have reported like GDCRO3, YFEO3, YCRO3, YMNO3, TBFEO3, TBCRO3, GDMNO3, and actually published a good number of the papers over these applications, like actually for photochemical and the electrochemical hydrogen production. We have actually also made some actually dope oxides, which actually we have applied for the multifunctional application, not only for the hydrogen production, we have also applied for the organic transformation reactions. So we are also actually looking for the different kind of the interesting material which could be actually useful in like actually the different kind of the properties. Like actually we have actually added several reports based on actually amines, POPs. So because actually these materials are very important, because actually if you make the heterostructures of these materials, then actually they could give actually very interesting and very important results. We have also actually added some reports over the MOX, COX for CO2 reduction and hydrogen production, and the graphene-based derivatives for energy conversion applications, flatland materials, then the nitrogen reduction catalyst, also very, very important, very recently actually accepted in small. And we have also actually made some supramolecular complexes or the inorganic complexes, and we have shown that actually the complexes which are actually listed in the inorganic chemistry, they are also very actually useful for the hydrogen evolution reaction, and we have actually achieved very interesting results in this problem. So to conclude my presentation, MIT-free semiconductor graphite carbon nitride was actually taken as the binary support due to the high electrical conductivity and the high surface area. The metal oxides, sulfides, and selenides were interfaced to design GCN-based multifunctional heterogeneous catalyst for effective charge transfer and efficient solar water splitting for scalable hydrogen production and high electrocatalytic HER performance. Highly porous advanced materials or layered materials are more favorable for carbon capture. Scalable green hydrogen production reduces greenhouse effect and favors net zero carbon emission by carbon neutrality for a sustainable environment and future. So for this kind of the work, actually, I must be thankful to all my hard-working PhD scholars. So till date, actually, 16 PhD scholars have actually received PhD degree under my guidance. Presently, 11 PhD scholars are working under my guidance in my research lab. I must thank to all my collaborators like Professor Chari Rowan University, Professor Mao, Illinois Institute of Technology, Chicago, Professor Shahri and Professor Ahmad at King Saudi University, Saudi Arabia, Professor Ingole, Professor Chaudhary, Professor Samir Sapra at IIT Delhi. And the funding agencies, actually, all Indian funding agencies, they are actually supporting to my lab, like DST, CRB, CSIR, Spark, and of course, actually my university. So uh, uh, I also actually, this is my actually recent statistics, I mean, present actually today's statistics based on the research, actually citation, H index, I-10 index, and I'm going to get actually the next Dr. Sanjay Pandey Award. So a lot of actually awards, medals actually I have achieved in the past few years. So because of actually this work, because of my students, collaborators, for that actually I'm always very, very thankful. And I'm also thankful to all my audience actually who are very patiently listening me and actually promoting our work. I was thankful to the organizers actually for inviting me to this interesting platform.